Okay. Let's go. So first, let me tell you the objective. So, as you know, programmers use different naming conventions when they write names. Will it be camel case or underscores or caps or whatever? There are a few very crazy naming styles. Anyway, if we want to split the name by following this naming convention, it will be very easy. But what happens if everything is, let's say, lowercase, or everything is capital case? Then the task will be not so easy because we don't know that foobar and bus, as in this example, are really different. So we want to do exactly that. We want to train a machine learning model which splits this all lowercase identifier. And it has at least 3 applications. So first is most practical one, which we use in our company. It reduces the core vocabulary size, which you reach after splitting. As I will show later, more than 60%. It's really considerable. You can use this model to automatically fix names while you type. Imagine that you missed a shift button and the letter will be automatically capital. Or you can just forget about shift and just type as you type, and your naming convention will be automatically applied. It's just an idea. I mean, the third one, we never implemented it, but it's still possible, I guess. So, as all machine learning problems, it all starts with a data set. So, our data set is public Git archive. It contains 182,000 repositories from GitHub, so it's quite a huge one. Takes 3 terabytes on disk. It's not easy to process. Also, it has, as you see, it has 16 billion lines of code. Compared to Google, who has 2 billion, it's 8 times bigger. And actually, it's just a single fraction of what we have on GitHub. We are able to release a bigger data set, but it would be even harder to process. So we decided to just fix on this 182,000. Why this number? Because we picked all repositories which are at least 50 stars on GitHub. So based on this data set, we extract identifiers from the header revision of all the projects. Then we split them by naming convention. And we say that this is our training set, and this is how we should split. So we pretend that the initial identifier is all lowercase, and we already have the labels. So this is how we train our model. To do this identifier extraction, we apply an AST parser and a regular expressions parser. The thing is, AST parser is very precise. It never makes any mistakes. So in our case, we use Babelfish. But it doesn't support all the languages. And GitHub has more than 400 languages. And we want to parse all of them. So for some kind of exotic ones, we use pigments as it is regular expression based. And the problem here is that if you want to use a regular expression parser, it is going to make mistakes just because it doesn't know much about the context, about the structure of the source code. So we had to manually write some rules to filter the noise after regular expressions. And our data set, which we release, is 49 million distinct identifiers. Then we split them. And 7%, a bit more than 7% are not splittable. It means it's just a single part. We cannot do anything with them. It doesn't mean that those identifiers are necessarily bad. Of course, they're not. But it's just a single part. We cannot use them as labels. So we throw them away. And the rest, 20%, become the same sequence after splitting. Just because the different cases just normalized and become the same sequence, or also we throw away numbers, we throw away any non-alpha characters. So this is how we have. So big amount of aliases. We reached 35 million after this step. All right. So this just illustrates what we do. Then we apply the length threshold because we're not interested in very long identifiers. Just because when we train our models, we usually place some constraints on the identifier length, and we don't want to do extra steps to support very long ones. We are not interested in them. Also, the number is not so big. It's only 1 million. We can just sacrifice it for the sake of doing our job very fast. So we apply 40 characters length limit because, as you see on the histogram, the peak is roughly 15. So most of the identifiers are 15, 16 characters. And this distribution has a long tail. We cut at 40. That's it. So regarding the naming convention splitting, as I said, we have a number of heuristics to do the splitting, and these are the examples how it works. As you see, for example, we split by underscore, or we split by this case change, and so on and so forth. So we have the source code to show if you're interested. Yep, and we release this dataset. Also, we release separate datasets with identifiers extracted for specific languages, for Java and so on and so forth, just in case people are interested in looking what is the difference between Java identifiers and, for example, Python identifiers. And it was interesting for us to plot this language intersection between using identifiers. So the number at the intersection of Python and JavaScript, for example, shows how many distinct identifiers are the same in both languages. And since our data set is big enough, it's kind of representative. So you can see which languages are related and which languages are not so related in terms of, let's say, naturalness of identifiers. All right. And once we have the data set, we start training baselines because we want to compare our proposed model to a number of solutions which are supposedly not so good. So the first baseline which we trained is on smooth character level model. It's pretty basic. We just say that the probability of a split depends on the prefix, and we read the identifier character by character. So in our case, we had depth set to 11, and also because it was on smooth, it was rather big, so it was a few gigabytes in size, so we cannot increase the depth. I guess if we would make it smooth, we could increase the depth. So also you can read identifier from left to right and to right to left, and it's basically no difference. So the question is how you are going to use the both predictions at once, because you have one model left to right and one model right to left. You can either merge them using AND condition or by OR condition. This means that if both models predict that there is a split, then there is a split. If at least one is not sure, you say that this is not a split. And in case of OR, you say that if at least one model predicts that there is a split on the certain place, you say that this is a split. The second model is called dynamic programming. We are not sure about the proper name actually, because the implementation which we used doesn't mention any research on that. But the idea is very simple. You just build a tree of all possible splits inside of the identifier, and you have a cost or penalty for every split, just based on the probability of the corresponding subtokens to appear in your data set. So we trained 3 models based on this idea. one uses probabilities from Wikipedia, and also we use the vocabulary from Wikipedia. Supposedly Wikipedia's vocabulary is broader than the source code identifiers. As we found out later, no, it's not. The second was based on the Zipf's law, prior assumption of the probabilities of each subtoken. And the third model is just using the distribution of subtokens which appeared in the final dataset after splitting. The next model is based on decision trees. So this is an example how it works. You have foo-bar bus, and let's say that we want to understand if there is a split between B and A. So we represent every letter as a number. It's very easy. You just use the character index. And then you feed these 8 characters to a decision tree or a decision tree forest. And they predict if it's 0 or 1. So if there is a split or there is no split. In our case, we use XGBoost as a very solid implementation of decision trees. Also, they are boosted. We used window length of 10, and we could not actually sample all possible non-splitting places because it would take too much time to train. XGBoost just doesn't work so fast for us. So we decided that we will use 80% negative samples. So we're not going to use all places, just some randomly sampled 80%. And the final model, which we use as a baseline, is a character level CNN. We one-hot encode every character, and we use a stack of 3 layers, one-dimensional layers, which were inspired by Inception. And finally, we place a time-distributed, fully connected layer on top. So each CNN layer looks roughly like this. You have one-hot encoding for 32 dimensions, because you have roughly 20-something ASCII characters. And just for the sake of the future layers, we decided that we will fix 32 for everything. And you have the window size set to 40. You apply batch normalization, then you apply 4 independent convolutional kernels. One is of length 2, one is of length 4, 8, and finally 16 characters. And you also change the number of these kernels. Here you have 64 kernels, 32 bigger ones, 16 bigger ones, and 8 kernels of size 16. You concatenate them, then apply batch norm again, and finally do dimensionality reduction convolution as Inception does. And you get the same output as the previous layer, so exactly 40 by 32. So you stack 3 layers like that, and finally fully connected layer, and you predict binary labels at every character. All right, so now the model which we think works the best on our dataset is bidirectional LSTM. This is how it works. You have characters of your identifier, XF, so on and so forth. I think it's foo bar here, yes. And you have 2 LSTM layers which kind of go in front of each other. So one from left to right, one from right to left. And at every position, you concatenate the output of the corresponding cells. And then you predict if it's 0 or 1. So once you read the whole sequence in both directions, you predict 0 or 1 at every position. So this works considerably faster and better than just using a regular LSTM, where you just regular character level LSTM, because in that case you would have to read all the prefix and then forecast or predict. It just takes too much time, and this is much more performant. So we used two stacked layers, one on top of each other, and each layer had 256 neurons in our case. So actually, let me update it because, yep, it should be 15 hours. So we train for 10 epochs, and it takes 15 hours. Just to compare to a character level CNN, it trains twice as slower, and we use 2 GPU cards. So let me show you how all these baselines in our BLSTM perform. We use 80% training identifiers and 20% validation, and we measure precision, recall, and F1 score. It turns out that BLSTM works the best. At the same time, we also tried GRU because it's roughly the same but a bit different inside. BGRU performed a little bit worse. Then character level CNN reaches 1% less precision and recall. And also you see that dynamic programming solution actually performs better than gradient boosted trees. And it's not shown the language models which are unsmoothed, actually because they perform so bad. I can show you the table. So as you see, the one which has the OR condition model, it is very imprecise, obviously because noise multiplies many times, but the recall is excellent. It's really good. At the same time, again, if you merge the models using AND condition, you have very good precision, but recall is very bad, obviously because you miss a lot of potential splits. Dynamic programming works best with the factual distribution of your subtokens in the dataset, so posterior distribution, and it reaches 93% precision, 89% recall. Boosted trees performed not so good for some reason. We will have to investigate why, but it was worse than CNN, and LSTM reached almost 95% in both precision and recall. I think recall is even 96%, which is good. So I would say that it is possible to use CNN if the environment requires a very performant model. If you are not constrained with performance, BLSTM would be the best choice. So now I show you how we reduced the core vocabulary size, as I promised in the beginning. You start with 49 unique identifiers. Then, as I said, some of them are not splittable by our naming convention heuristics. And the number is 1.8. And when you apply your trained model to these identifiers, you get only 500,000 identifiers. So you reduce the vocabulary roughly more than 3 times. And as for the ones which were splitted, you reduce the vocabulary 2 times. And once you merge both branches, because you're interested in all identifiers, not only those which are splittable or not splittable, you go down from 2.9 million to 1.1 million, which is 60-something%. And it is very important because we embed identifiers using an explicit co-occurrence matrix-based embedding algorithm, and it scales with the vocabulary size, and it is able to process 1 million in, let's say, sane amount of time, a few days, but 3 million would take us a month, and it unfortunately isn't possible. So to summarize, we extracted a data set of 49 million distinct identifiers from PGA. To our knowledge, it is the biggest data set with identifiers to date. We used the naming convention heuristics to generate the label data set, which we train our models on. Then we train baselines, and our LSTM performs the best. And also, we were able to reduce our core vocabulary size more than by 2 times. As for future work, it makes sense to bootstrap the training in a sense that, as I showed, after splitting with heuristics, it's still a possibility, an opportunity to apply your trained model and go deeper, produce more splits. So we can do that and then train a new model on top of the properly splitted data set. And the second model is going to perform better, in our opinion. Also, we discard all non-alpha characters. We discard numbers, we discard underscores, dashes, so on and so forth. And it's not good for all the cases. So I guess sometimes it is important. So we can repeat this, but not throwing away these characters. And yep, actually, I'm very close to finish. And since I have a little bit more of a time, let me show you the way we actually embed identifiers from a different presentation. So consider this source code snippet. In this case, it's Python. We extract identifiers from this snippet. Also, we split them and we stamp them to reduce vocabulary size as much as possible. And we start with the outer scope. And these are the identifiers which we extract. Some of them appear more than 1 time. And for example, here connect appears 2 times. Same with user, password, so on and so forth. Then we traverse. So the nodes correspond to the extracted tokens, and the thickness and brightness of every edge is corresponding to how many times this pair of identifiers occur together in the same context. We traverse.
What's in the same context?
So it's just what is inside this dashed rectangle. So this is a context. Basically, visibility scope. Let's say all identifiers here are kind of in the same visibility scope, just because they are under the same AST node.
If you had AST node for the whole file, then wouldn't everything be the same?
Yep. Yeah, that's right. It is another context. That's right. That's totally correct. So we traverse the AST, and we just go to a particular function, do exactly the same, and increment the corresponding values of co-occurrence. And as you see, some of the edges become brighter because these identifiers appeared in the same function. Then we go to the corresponding AST node, which defines the function declaration. Extract the same, increment, then we go line by line, we scan the function, do the same thing until we finish traversing the AST. And we end up with a graph with all possible tokens extracted from all the files in our dataset. And this graph can be represented as an incidence matrix. And we apply, incidence matrix, which is called the co-occurrence matrix in some papers which are related to machine learning and embedding on explicit matrix. And it is proven that the regular word2vec does the same thing as an explicit embedding algorithm. It optimizes for pointwise mutual information. So we say that if we calculate the scalar product of our embedding vectors as the pointwise mutual information, which is calculated in turn from the cells of our concurrence matrix. We have a proper embedding with all the properties which you would expect from an embedding. So we can do associations, you can do clustering, they are grouped together, so on and so forth. So this is how this matrix looks like. You have a tiny core of identifiers which occur together very frequently, and actually it's very sparse. The majority doesn't occur with each other very often. So to properly embed it, we shard it. It's the way Swivel works. So Swivel is a way to embed an explicit matrix from Google Research. There is a paper about it. It scales really well, and yep, we used it to generate the embeddings. I'm skipping this and just pass over to the results. So in this case, our splitting was not so perfect. And if you look for identifiers nearest to foo, you not only get metasyntactic variables, but also you get a lot of prefixes. It works for normal ones. The results are a bit better. As I said, you can do analogies. So yeah, send to receive, pop is to push, the same here. And also, since developers tend to spell words differently, also sometimes they just make typos. The receive and receive with letters swapped appear very near each other in the same neighborhood. Okay. So this is all I wanted to say. Also, we have a Github repository where we maintain all the research papers about machine learning on source code. I guess ML for programming is the same. It has more than 3,000 stars, so it's kind of popular. If you have a good suggestion for a paper to post there, please do that. We are open to pull requests. Also, we have a community of researchers from industry. We have security engineers from Apple, from Google. And if you're interested in this topic, join the community on Source Tech. Thank you.
Just one quick question.
Yep.
When you do this collection of identifier splitting, do you differentiate the different phenomena of human language, or for example, object-oriented language?
So for our tasks, we did not, but since we released the dataset per language, it is totally possible to train a specific model for every language and compare them. It would be interesting. We didn't do that.
I might have missed it, but did you compare the EMI factorization to just running Word2Vec directly on the code?
So we would really love to, but Word2Vec would work for a few months on our data, and we didn't want to wait so long. Because Word2Vec scales with the dataset size, and Swivel scales with the vocabulary size, so it's a bit different.
A quick question. So, do you try baseline, which is just like splitting on underscore capital letter? Maybe I missed it.
So we used heuristics as the ground truth, and we said that this is what we want our model to work like. And our baselines were working on just all, let's say, lowercase identifiers without splitting.
But I mean, why? What's the justification for that? What if in practice it's enough to split on?
You mean why do we have to do that? So as I said, it is critical to reduce the token vocabulary size because some of the algorithms, for example, our identifier embeddings, also I know the topic modeling is the same. It requires as smaller vocabulary as possible. just for performance reasons.
I think there's an assumption that you need this approach because detecting heuristically that something is camel case or separated by underscores would not do good enough job for all the identifiers, right? So, but that is something that you could test empirically. I think that's what Mark's question was.
Yeah, actually we use it as a second step. So first we apply heuristical split, and then we apply the model on the splitted subtokens, and then we split them further. And this is the thing which allows us to reduce the vocabulary size. So in theory we could compare. I agree with that. We just make everything normalized and we apply heuristics, but it is the same as comparing your trained model on the trained data set. It would be very good, like 99% accuracy or something. All right.
No, then
Some other question.
yeah. Oh, sorry.
So I didn't understand, like, so after you do this, you reduce the vocabulary size and it's faster to train, right? Because it gets smaller size.
Let's say upstream models are considerably faster to train. Yep.
Very faster. So what are some of the clients, maybe I missed this, like that you're using the model for?
You mean upstream model for identifier embeddings?
For identified embeddings?
Is this your question? How do we use the identifier embeddings model?
Yeah, what do you do then? What's the client after this?
Right. So we apply it for a number of tasks. For example, we have a very nice application. We extract identifiers for every GitHub repository, represent each repository as a weighted bag of identifiers. And then we apply a word movers distance metric to compare repositories between each other. So basically say if the identifier sets intersect much, repositories are similar. It's of course it's more complex than that because the distance metric is using linear programming to take into account the weights, the embeddings. Then you have your query repository and you have a database of all open source repositories on GitHub, and you ask which repositories are similar to this one. And after waiting for a few minutes, you get the result. And in our case, it worked really well. So if you query for TensorFlow, you would find other deep learning frameworks in different languages. If you would query for a specific compiler, you would get related compilers. If you would query for, I don't know, beer repositories, you will get all repositories related to beer. So it worked rather universally.
Okay. Good then. So let's thank our speaker again.